Hello and welcome to AI for Developers. I'm Chaitanya talking bot. Today's lesson is titled Q Learning and Policy Gradients. Your first steps into RL algorithms. Imagine teaching a robot to walk, or an AI to play a complex video game. Not by programming every single step, but by letting it try things and learn from its mistakes. Just like we do. That's the magic of reinforcement learning. RL. As developers, this opens up a whole new world, creating smart agents that can make decisions in dynamic environments. From optimizing supply chains to driving autonomous cars, it's about building AI that truly learns to act and adapt. Every RL problem has a few key players. Think of it like a game. Your eye is the player, and the world is the game itself. Agent. This is your eye program. The player in the game. It makes decisions. Environment. This is the game world itself. It reacts to the agent's actions and provides feedback. State. What the agent observes about the environment right now. E.g., its position on the board, current score, sensor readings. Action. A move the agent chooses to make. E.g., move left, jump, attack, turn a valve. Reward. The feedback the environment gives the agent after an action. E.g., plus 10 points for picking up a coin, minus 5 for hitting an obstacle, a bonus for completing a task. The loop. Agent observes state right pointing arrow chooses action right pointing arrow environment reacts. Provides new state and reward. This cycle repeats. Q learning is one of the simplest and most foundational RL algorithms. Imagine you're playing a simple game, like finding your way through a maze. Instead of knowing every rule beforehand, you want to build a cheat sheet that tells you, for every possible situation, state, which action will lead to the best long-term outcome. This long-term outcome is called a Q value. Your AI agent will learn these Q values, essentially filling out a giant table, the Q table, of state action pairs and their associated value, guiding it to the best path. How does the AI fill out this cheat sheet? It plays the game. 1. Explore and exploit. Sometimes it tries random moves. Explore. To discover new paths and learn new rewards. Other times, it uses its current best cheat sheet. Exploit. To pick what it thinks is the best action. 2. Update Q values. After each action, it gets a reward. It then uses a simple update rule to adjust the Q value for the action it just took, considering the immediate reward and the potential future rewards from the next state. This gradually makes the cheat sheet more accurate over many iterations. The goal is to eventually have a Q table that, for any given situation, reliably points to the action that will maximize future rewards. Q learning is great for simple games or environments with a limited, countable number of possible states, situations, and actions. Think tic-tac-toe or a small grid-based maze. But what if your game is a complex 3D world with millions of possible camera angles, object positions, and character states? Or controlling a robot arm with infinitely many joint positions? The Q table would become astronomically huge, impossible to store in memory or to learn efficiently. This is where we need a more sophisticated approach than simply memorizing every single scenario. Instead of trying to memorize the value of every single action in every single state, which a Q table does, policy gradients take a different, more flexible approach. They aim to learn a policy directly. Think of a policy as a brain or a general strategy. Given any situation, it directly tells the agent what action to take, without needing to look up Q values. This brain is often represented by a neural network, allowing it to generalize across similar, but not identical, situations. When the agent acts and gets a reward, the network slightly adjusts its internal weights, its decision-making logic, to favor actions that led to good rewards and avoid those that led to bad ones. Policy gradient algorithms learn by trying actions and then tweaking the policy based on whether the whole sequence of actions, an episode of gameplay, like an entire game round, was good or bad. If a series of actions led to a win, the brawn is slightly adjusted to make those actions more likely next time. If it lost, those actions become less likely. Here's when you might choose one over the other. Q-learning. Simple, table-based, or function approximation for larger states. Great for discrete, countable states and actions. Can be very sample efficient. Learns fast. Policy gradients. More complex. Uses neural networks. Handles continuous states and actions naturally. Scales better to complex environments. Often learns more natural, behavioral policies. As a developer, understanding these foundational differences helps you pick the right tool for the job. Whether you're building a simple game AI or tackling a complex robotic control problem. Thanks for watching. If you found this helpful, make sure to subscribe to our channel and hit the like button.